So hyperplane is subspace whose dimension is one less than the original space. So essentially we can define hyperplane for any real p-dimension space, and the hyperplane dimension is p-1 in general. So in the previous case, we defined hyperplane in the 2D space where the hyperplane is just a linear line. This is 1D space. Okay. And the hyperplane usually defined with parameter beta 0 and beta 1 up to beta p. And the equation beta 0 plus the inner product between beta vectors and x point equal to 0, and all x values satisfy this equation consists the hyperplane. Okay, and here the beta vector, of course, consists of p number of parameters, beta 1 to beta p, and x vector as well. Okay, so the hyperplane equation, this equation has very nice property, and it contains many important information. For instance, we can easily compute the distance between a point and hyperplane from this equation. Okay, so let's go back to the 2D space case. So there is x1 and x2, and there is some hyperplane here, and the equation is beta 0 plus inner product between beta vector and x vector equal to 0. And let's say let's assume we want to measure the distance between the original point and this hyperplane, this distance. How can we compute the distance? So to calculate the distance, we have to find this point, which is the closest point to the origin, and we have to compute the L2 distance between the original point and the closest point. So this looks complicated because we have to find the closest point to the origin point, and I don't like this method, but we have much simpler method that can measure the distance to the original point. How can do that? So before computing the distance, I want to first explain the concept of inner product and projection. When you have a point, a comma b point here, and there is two axes, x1 and x2, you can easily understand the x1 element when you project this vector a comma b onto this x1 axis. This point is a comma 0, and the length from the origin to the a comma 0 is just a. When you project a comma b to x2 axis, again, you can very easily understand the projected point. This is 0 comma b, and the length from the origin to this point is just b. Okay. In this, you can compute this a comma 0 element from projection matrix. This axis can be represented with a unit vector share the same direction, 1 comma 0. This direction can be represented with a unit vector share the same direction, 0 comma 1. And 1, 0 and 0, 1, they are standard basis vector. These two vectors can represent any vector or any point belong to the 2D space, right? So with any vector, with any a, b, when you compute the inner product between the basis vector, unit vector, and the vector a, b, then you can obtain the length. So when you actually take the absolute value of this inner product, you can simply get the length when you project a vector onto the x1 axis. Likewise, you can simply calculate the length when you project a vector onto the x2 axis by computing the inner product between 0, 1 and AB. Of course, you have to take the absolute value here. Right. And when you multiply the unit vector one more time, then you can obtain this a, 0 vector, the projected vector when you project a, b onto x1 axis. So when you multiply a, b onto this matrix, 1, 0, 0 times ab, because this is inner product between 1, 0 and ab, and multiply to the unit vector again. This is equal to 1, 0, 0, 0, 0 times a, b, and this is equal to a, b, a, 0. Sorry. Okay, so this is called projection matrix. When you have a unit vector, then the original unit vector times the transpose of your unit vector that compose a projection matrix. So when you multiply any vector onto this projection matrix, you can easily obtain the projected vector onto the target space. Okay, so let's go back to the 2D space case. Why I explain this? To understand the distance between the origin point and this subspace, this hyperplane, beta 0 plus inner product beta and x vector. So when you take any vector, any point here, and take the vector this from origin to this point, since you know the orthogonal vector, there is orthogonal vector onto this line, beta 1, beta 2, right? The beta vector, that is orthogonal vector to this hyperplane, which I explained, right? So the inner product between this red vector and the beta vector can tell you the distance between the origin point and the hyperplane. Not always when the ranks of beta vector equal to 1. When beta is unit vector, then the inner product between this red vector and the unit beta vector will tell you the projected ranks here. Projected vector here. Okay. So we almost reached to the answer. So the hyperplane is defined with this equation. And by simple scaling, you can make a unit beta vector. How can we do that? It's very simple. Since the right-hand side is just 0, you can divide with any constant. Still hold. Okay? And then this is the distance to the original point. Of course, you have to take the absolute value here. Okay? This is the distance to the origin. Okay, then how about some other point, not origin, but some outside of the hyperplane? How can we calculate the distance to this hyperplane? How can we do that? Same. It's same. So when you have this point, let's say this point is A, B, right? And this you can define any vector with any point here on the hyperplane. Let's say this is x1, x2. Okay. Then what is the distance? The distance will be a minus x1, b minus x2, and beta vector, normalized beta vector, inner product. Because this is unit vector, when you take the inner product, then the inner product will tell you the ranks when you project this vector onto this orthogonal plane. So you will have the length of this vector. Start from A, B and go to this hyperplane with orthogonal angle and end at the cross point. And this inner product will tell you the length between A, B and the hyperplane. Okay, and what is this? You know x1, x2, beta inner product is equal to minus beta 0 normalized beta vector. We already know this. So from this, the let inner product is equal to AB inner product beta over 2 normal beta vector plus beta 0 over the length of beta vector. That's it. Okay. So this is the bottom line. When you define fx like this, beta 0 over beta vector plus beta vector over the ranks of beta vector, so normalized beta vector, and x inner product. Then fx itself tells us the distance to the input x from the hyperplane defined with this fx equal to 0. Distance to the hyperplane fx is equal to 0. When you put any point outside hyperplane, you can easily obtain the distance to the hyperplane fx equal to 0 using the function fx. Of course, you have to take the absolute value. And essentially, the sign of fx also very important. The sign of fx will tell you which side your point located. Upper side or downside, left side or right side. So the sign of fx tells you which area, this area or this area. The sign of fx will explain the position.